Welcome to Scientific Serenity. Tonight, we embark on a journey not through space, but through the very idea of space. We will explore a concept that lives at the border between mathematics and mythology, a ghost in the equations of the universe that suggests our cosmos might be punctured with shortcuts, tunnels through the impossible. This is the story of the wormhole. But before it had a name, before it was a staple of science fiction, it was a phantom, a curious, almost discarded solution in the margins of the greatest theory of gravity ever conceived. Our story begins in 1915 with Albert Einstein's general theory of relativity. This was not merely a new theory of gravity. It was a new theory of reality. Einstein proposed that gravity is not a force pulling through space, but rather the curvature of spacetime itself. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move. The sun creates a depression in the cosmic fabric, and the planets roll along the contours of that depression. The equations of general relativity are notoriously complex, a set of interlinked differential equations describing how geometry responds to matter. Finding exact solutions, specific configurations of mass and geometry that satisfy the equations, became the primary work of theoretical physicists. The first and most famous solution came from Karl Schwarzschild in 1916, describing the space-time around a single, non-rotating mass. It contained the seeds of the black hole, though this was not understood at the time. For nearly 2 decades, physicists explored other solutions. Then, in 1935, Albert Einstein himself, working with his younger colleague Nathan Rosen at the Institute for Advanced Study in Princeton, found something peculiar. They were attempting to construct a purely geometric model of a fundamental particle, like an electron, using only the gravitational field, an effort to unify gravity and electromagnetism. In their mathematical exploration, they derived a solution that described a bridge connecting 2 separate, flat regions of space-time. Their paper, The Particle Problem in the General Theory of Relativity, presented this bridge as a mathematical structure. They envisioned a sheet of space-time, a universe, connected to another sheet by a narrow throat. This throat was not a hole punched through the sheet. It was a smooth, geometric tunnel, a seamless part of the fabric itself. Mathematically, it was a valid solution to the field equations. They called this structure a bridge, but it would later be known as an Einstein-Rosen bridge. The Einstein-Rosen bridge had peculiar properties. The 2 mouths of the bridge were actually the manifestations of what we would now call a black hole and a white hole. The bridge itself, the throat, was a moment of extreme curvature. Crucially, in their solution, this bridge was not traversable. It was not a tunnel you could travel through. It would form and then pinch off instantaneously, faster than any signal or object could possibly traverse it. It was a mathematical curiosity, a brief connection between 2 distant points that snapped shut before anything could use it. Einstein and Rosen saw it primarily as a model for a particle, not as a cosmic shortcut. The physics community of the 1930s received it as such, an interesting but likely non-physical artifact of the equations. The world was on the brink of war, and the minds that might have pondered its deeper implications were soon consumed by other, more terrestrial physics. The bridge faded into the background, another ghost in the vast mansion of general relativity. Yet the idea of connected geometries would not die. It lingered in the mathematical subconscious of theoretical physics. If space-time could curve, could it also fold? Could two distant points be brought together not by moving through space, but by moving through a higher dimensional fold in the fabric? The Einstein-Rosen bridge was the first hint that the answer might be yes, but it was a flawed and non-traversable hint. The true nature of this bridge, and its transformation into the concept we now know, would require a new visionary, a physicist with a flair for dramatic language and an imagination as vast as the space-time he studied. That man was John Archibald Wheeler, and his arrival would give the ghost a name and a place in the scientific imagination. But that is a story for our next chapter. For now, as you listen, consider the profound shift in thinking that had occurred. Before Einstein, space was a static stage. After Einstein, it was a dynamic, malleable entity that could bend, warp, and perhaps even connect to itself in strange loops. The universe had become a geometric object, full of hidden structures waiting to be discovered in the mathematics. The Einstein-Rosen bridge was the first whisper of a cosmos that might be woven together in ways far stranger than straight lines and distances. It was a suggestion that the shortest distance between 2 points might not be a straight line, but a tunnel. The Einstein-Rosen bridge remained a mathematical specter for over 2 decades, a curious footnote in the annals of general relativity. It was a solution in search of a physical interpretation, a bridge that led nowhere practical. The transformation of this ghost into a tangible cosmic concept, a wormhole, required a physicist who could see the poetry in equations and who possessed the courage to name the unnameable. That physicist was John Archibald Wheeler. Wheeler, a towering figure at Princeton, was a master of conceptual synthesis and vivid terminology. He had already played key roles in nuclear physics and had mentored legends like Richard Feynman. In the 1950s, his interests turned decisively toward gravitation and the deep mysteries of general relativity. He was fascinated by the extreme implications of Einstein's equations and began to explore the geometry of space-time with fresh eyes. In 1957, Wheeler, along with his student Charles Meisner, was investigating the quantum aspects of gravity. They were considering the nature of space-time at the smallest possible scales, at the Planck length. In this realm, Wheeler proposed, the fabric of the universe might not be smooth. Instead, it might be a chaotic, fluctuating foam, a quantum foam. Within this foam, he suggested, tiny topological structures could spontaneously form and disappear. Connections could briefly flash into existence, linking separate points in this microscopic chaos. It was in this context that Wheeler revisited the old Einstein-Rosen solution. He saw it not as a model for a particle, but as a prototype for a whole class of topological features in spacetime, and he gave it a name that would capture the public imagination forever: the wormhole. The analogy was perfect. Imagine an apple. A worm eating through the apple does not travel along the curved surface. It burrows a shorter, straighter tunnel through the fruit's flesh. Similarly, a wormhole would be a tunnel through the higher dimensional bulk of space-time, connecting two distant points on our three-dimensional surface. Wheeler's terminology stuck instantly. It was visual, intuitive, and evocative. The ghost had been christened. Wheeler made a crucial distinction. He differentiated between two broad types of wormholes based on their mathematical properties: Lorentzian wormholes and Euclidean wormholes. The original Einstein-Rosen bridge was a Lorentzian wormhole, a structure within the normal, real-time space-time of our universe. However, it was non-traversable. It collapsed faster than light could cross it. Euclidean wormholes, on the other hand, existed in imaginary time, a mathematical trick used in quantum gravity calculations. These were even more ephemeral, potential tunnels in the quantum foam that could influence particle physics, but were not pathways for macroscopic travel. Wheeler's work shifted the discussion. Wormholes were no longer just one odd solution. They were a potential feature of space-time topology, especially in the wild quantum realm at the universe's smallest scales. This conceptual leap opened a floodgate of theoretical inquiry. If wormholes could exist mathematically, could they be made stable? Could they be held open long enough for something, or someone, to pass through? The answer, it seemed, depended on the nature of matter and energy required to prop open the throat of the tunnel. General relativity has certain energy conditions that ordinary, familiar matter, what physicists call classical matter, always satisfies. These conditions essentially say that energy density is non-negative and that gravity is always attractive. If you try to construct a traversable wormhole using only ordinary matter, the equations show that the throat would pinch off catastrophically. The bridge would snap. The negative pressure required to keep it open against its own intense gravitational pull simply does not exist in the catalog of normal materials. Therefore, a stable, traversable wormhole would require what Wheeler and others began to call exotic matter. This is not merely antimatter or dark matter. Exotic matter, in this specific technical sense, is matter that violates the so-called null energy condition. It would have a negative energy density, creating a kind of gravitational repulsion or negative pressure to counteract the wormhole's tendency to collapse. In the 1960s and 70s, this seemed like a pure fantasy, a theoretical device with no counterpart in reality. However, a glimmer of hope came from an unexpected corner of quantum physics, the Casimir effect. Predicted in 1948 and measured with increasing precision in later decades, the Casimir effect occurs when two perfectly conducting, Uncharged metal plates are placed extremely close together in a vacuum. Quantum field theory states that even a perfect vacuum is not empty. It teems with virtual particles that constantly flicker in and out of existence. The plates restrict the types of quantum fluctuations that can exist between them, leading to a lower energy density in the gap than in the surrounding space. The result? A measurable attractive force between the plates. Crucially, between the plates, the energy density of the vacuum is effectively negative relative to the free vacuum. This was a real, laboratory-demonstrated instance of negative energy density, the very stuff needed, in principle, to stabilize a wormhole's throat. The amount was infinitesimally small, but the principle was proven. Exotic matter was not completely forbidden by the laws of physics. Quantum mechanics permitted it in controlled, microscopic amounts. By the late 1970s, the wormhole had evolved from Einstein's geometric ghost into a structured theoretical possibility. It had a name, a classification, and identified key problem. Stability required exotic matter. The next great leap would come from a physicist who would take this problem head-on, asking not just if wormholes could exist, but how we might actually build one. That physicist was Kip Thorne, and his work would bring wormholes crashing from the realm of abstract theory into the domain of plausible, if staggering, engineering. It would also reveal their most mind-bending property, the potential to manipulate time itself. The stage was set. Wormholes had a name, a theoretical foundation, and identified central problem. They were catastrophically unstable. To transform them from fleeting mathematical phantoms into potential cosmic shortcuts would require a radical ingredient, exotic matter with negative energy density. As the 1970s gave way to the 1980s, the quest entered a new, more daring phase. It became a structured engineering problem within the framework of theoretical physics. The man who would lead this charge was Kip Thorne at the California Institute of Technology. Thorne, already a leading expert in general relativity, was approached in 1985 by his friend and colleague Carl Sagan. Sagan was writing his novel Contact and wanted a scientifically plausible method for his protagonist, Ellie Arroway, to travel vast interstellar distances. He asked Thorne, was there any conceivable way, within the known laws of physics, to achieve faster-than-light travel or its effective equivalent? Thorne, along with his graduate students Michael Morris and Ulvi Yurtsever, took this as a direct challenge. They decided to systematically investigate whether a traversable wormhole could be constructed without invoking unknown or magical physics. Their groundbreaking 1988 paper, Wormholes, Time Machines, and the Weak Energy Condition, published in the journal Physical Review Letters, changed everything. Morris, Thorne, and Yurtsever did not just rederive old results. They designed a specific, detailed blueprint for a traversable wormhole. They described a spherical throat, a smooth tunnel connecting two distant regions of space. Most importantly, They precisely calculated the properties of the material needed to line this throat to keep it open. Their model required exotic matter distributed in a thin shell around the throat, exerting enormous negative pressure to counteract the gravitational collapse. The amount of exotic matter required, while astronomically large by human standards, was not infinite. It was proportional to the size of the wormhole's mouth. A 1-meter wide wormhole might require the negative energy equivalent of Jupiter's mass. This was staggering, but it was a finite number, a calculation. It meant that, in principle, if you could somehow procure and manipulate such exotic matter, you could build a wormhole. The paper also made another startling, almost casual observation. If one mouth of the wormhole could be moved relative to the other, or subjected to different gravitational potentials, a time difference would emerge between them due to the effects of special and general relativity. By moving one mouth at high speed and then bringing it back, or by placing one mouth near a strong gravitational field, you could effectively create a time machine. Walking through the wormhole in one direction could take you into the past relative to your starting point. The traversable wormhole was not just a space shortcut. It was a potential gateway to time travel. This revelation brought the discussion crashing into the realm of paradox. Time travel introduces infamous logical contradictions, like the grandfather paradox. What if you go back in time and prevent your own grandfather from meeting your grandmother, thereby preventing your own birth? How could the laws of physics permit such inconsistencies? Thorne and his colleagues, along with other physicists like Igor Novikov, began to explore possible resolutions. Novikov formulated his self-consistency principle, which essentially states that the laws of physics will always conspire to prevent paradoxes. You could go back in time, but you could not change the past in a logically inconsistent way. Your actions would already be a part of the history that led to your journey. Your attempt to shoot your grandfather would inevitably fail. The gun would jam. You would miss. Some intervention would occur. The timeline would be self-consistent, not mutable. Stephen Hawking entered the fray with his chronology protection conjecture. He argued that the laws of physics, particularly quantum effects, would always act to prevent the creation of a time machine. Any attempt to construct one, say, by stabilizing a wormhole, would trigger a runaway feedback of quantum particles circulating through the time loop, building up infinite energy that would destroy the wormhole before it could be used. Hawking famously declared, "The best evidence we have that time travel is not possible, and never will be, is that we have not been invaded by hordes of tourists from the future." By the end of the 1980s, the wormhole was no longer Einstein's forgotten ghost. It was a central player in deep debates about the nature of causality, quantum gravity, and the fundamental structure of reality. It had become a laboratory for thought experiments, testing the limits of our physical theories. The simple bridge from 1935 had evolved into a nexus connecting the physics of the very large general relativity with the physics of the very small quantum mechanics. As you listen now, consider the extraordinary journey of this idea. Born as a geometric model for a particle, named after a tunneling worm, and engineered into a potential time machine, the wormhole represents the power of pure thought to explore the cosmos. It teaches us that our universe, as described by our best mathematics, might contain structures far stranger than we can directly see. Structures that challenge our understanding of space, time, and possibility. We have not found a wormhole. We may never find one, but the pursuit has illuminated dark corners of physics, forced us to reconcile relativity with quantum theory, and expanded our imagination of what might be. The ghost in the equation has become a guide, leading us to the very edge of known physics and prompting us to ask what lies beyond. So, as this first chapter closes, rest with the knowledge that our universe is a geometric fabric, and mathematics hints that this fabric might be threaded with hidden tunnels. They may be forever beyond our reach, or they may be the destiny of a far future science. For now, they exist in the sublime landscape of human curiosity, a testament to our desire to find shortcuts not just through space, but through the nature of reality itself. The Einstein-Rosen bridge was a skeleton, a mathematical structure waiting for flesh, context, and a name. For over 20 years, it remained a curious but isolated solution, a bridge connecting nothing to nowhere in the minds of most physicists. Its transformation into the dynamic, evocative concept of the wormhole required a visionary who could see the larger picture of spacetime's architecture. That visionary was John Archibald Wheeler. This chapter is the story of how Wheeler gave the ghost a name, a home in quantum theory, and a permanent place in the lexicon of cosmic possibilities. John Wheeler was a physicist of boundless imagination and linguistic flair. By the mid-1950s, he had already made seminal contributions to nuclear fission, helped develop the hydrogen bomb, and mentored a generation of brilliant minds. His intellectual journey was turning toward the deepest questions of gravity and quantum mechanics. He was haunted by a fundamental problem. How does the smooth, geometric spacetime of general relativity marry with the probabilistic, granular world of quantum physics? In pursuing this union, Wheeler began to think about the nature of spacetime at the smallest conceivable scale, the Planck length, about 10^3 meters. At this scale, the very concepts of before and after, here and there, become ambiguous due to quantum uncertainty. Wheeler proposed a radical picture. He suggested that space-time at this fundamental level is not a smooth continuum. Instead, it is a chaotic, turbulent, ever-changing entity. He called it quantum foam. In the quantum foam, topology itself becomes dynamic. Tiny wormholes, Einstein-Rosen bridges on a Planck scale, could spontaneously flicker into and out of existence. They would connect different points in this microscopic chaos, only to pinch off in a time spent shorter than the Planck time. The fabric of reality, according to Wheeler, was not merely curved. It was frothy, filled with ephemeral topological structures. The Einstein-Rosen bridge was no longer an oddity. It was a potential elementary feature of spacetime's microstructure. It was within this conceptual framework that Wheeler needed a new word. Einstein-Rosen bridge was cumbersome and too specific. It sounded like a static, engineered structure. He wanted a term that captured the dynamic, organic, and potentially tunnel-like nature of these connections, especially as they manifested in his foamy spacetime. The analogy he seized upon was perfect and timeless. Imagine an apple. An ant walking on the apple's skin must traverse the curved surface to get from one point to another. But a worm, burrowing through the apple's flesh, can take a shorter, more direct path. Similarly, a tunnel through the higher dimensional bulk of space-time could provide a shortcut between two distant points on our three-dimensional spatial surface. Wheeler called this a wormhole. The name was intuitive, visual, and sticky. It immediately conjured an image. With this single act of naming, Wheeler pulled the concept from the pages of obscure journals and planted it firmly in the scientific and popular imagination. Wheeler, with his students, began to classify these structures. He made a crucial distinction between two broad types, defined by their mathematical properties: Lorentzian wormholes and Euclidean wormholes. A Lorentzian wormhole exists within the familiar, four-dimensional space-time of our experience, 3 dimensions of space, and one of time treated as a real coordinate. The original Einstein-Rosen bridge was a Lorentzian wormhole. However, it was non-traversable. It contained a singularity and would collapse before any object could pass through. These were the wormholes one might imagine as cosmic shortcuts, though their stability was the central problem. A Euclidean wormhole was a different beast entirely. It arises in a mathematical technique called Wick rotation, where time is treated as an imaginary number. This transforms the space-time metric into a four-dimensional space with purely spatial geometry. These wormholes are not tunnels through time. They are instantons, saddle points in the path integral formulation of quantum gravity. They represent possible quantum tunneling events between different space-time geometries or topologies. In the 1980s, Stephen Hawking and others would explore how such Euclidean wormholes might affect the cosmological constant or the values of fundamental constants. They were not passageways for travel, but rather features of the landscape upon which the universe's quantum state is defined. Wheeler's work established the wormhole as a serious subject of study within quantum gravity. It was no longer just a solution to Einstein's equations. It was a probe into the quantum structure of space-time itself. If space-time was indeed foamy at the Planck scale, then wormholes, albeit unimaginably tiny and short-lived, were everywhere, part of the vacuum-seething texture. This idea led to a fascinating, if speculative, proposal. The space-time foam might be threaded with a network of these Planckian wormholes. Some theorists, like Hawking, suggested this foam could explain the vanishingly small value of the observed cosmological constant, the wormholes providing a kind of topological screening effect. Others pondered whether information falling into a black hole might be transmitted through microscopic wormholes, offering a solution to the infamous information paradox. Wheeler's contribution was therefore twofold. He gave the concept a powerful and enduring name, and he embedded it within the cutting-edge physics of his day. He transformed the wormhole from a static, classical geometry into a dynamic, quantum gravitational entity. He made it a symbol of the deep and turbulent marriage between the very large and the very small. The stage was now set. Scientists had a name for the ghost and a theoretical home for it in the quantum foam. The next great question was inevitable. Could these flickering Planck-scale tunnels be scaled up? Could they be stabilized, held open, and transformed from quantum ephemera into macroscopic shortcuts? Answering that question would require not just a visionary namer, but a brilliant engineer of spacetime geometry. That engineer would be Kip Thorne, and his work would bring the wormhole from the realm of quantum speculation to the edge of theoretical plausibility. Wheeler's conceptual framework of a foamy spacetime threaded with ephemeral wormholes was profound, but it resided in the domain of the infinitesimally small and the theoretically abstract. The Planck scale is 20 orders of magnitude smaller than an atomic nucleus. The wormholes flickering in that realm were not just tiny. They were manifestations of a reality where geometry itself was subject to quantum fluctuation. To bridge the gap between this microscopic chaos and the possibility of a traversable cosmic shortcut required a new kind of thinking. It required asking not just what is, but what could be if we had the means. It required turning the wormhole from a feature of quantum gravity into a problem of space-time engineering. This engineering mindset found its champion in Kip Thorne at Caltech. Thorne, a master of the rigorous mathematical application of general relativity, was approaching the topic from a different angle than Wheeler. While Wheeler was pondering the fundamental foam of space-time, Thorne was interested in the classical, macroscopic predictions of Einstein's equations. He was part of a generation that treated general relativity not as a completed monument, but as a tool for exploring extreme scenarios, black holes, gravitational waves, and now wormholes. The catalyst for Thorne's deep dive was famously a request from his friend Carl Sagan in 1985. Sagan, writing his novel Contact, needed a scientifically plausible method for interstellar travel that was faster than light, or at least provided its effective equivalent. He turned to Thorne, asking if wormholes could be the answer. Thorne, with characteristic intellectual generosity and rigor, took the question as a serious research project. He assigned the problem to his graduate student, Michael Morris. Morris, along with another student, Ulvi Yurtsever, began to systematically dissect the problem. They were not content with the old, non-traversable Einstein-Rosen bridge. They wanted to design, on paper, a wormhole that a human could theoretically pass through. Their guiding principle was minimalism. use-only physics that was known or considered plausible within the framework of classical general relativity and quantum field theory. No magic matter, no suspension of known law. Their results, published in the now classic 1988 paper, were a revelation. They presented a specific, mathematically detailed model of a traversable wormhole. It consisted of two spherical mouths connected by a throat. The geometry was smooth everywhere. There were no event horizons or singularities to rip a traveler apart. The curvature was gentle enough that tidal forces could, in principle, be made survivable for a human. The key to their design lay in the material required to line the throat, to prevent the wormhole from collapsing under its own gravitational attraction. The throat had to be threaded with matter possessing a very strange property, negative energy density. In their specific model, this exotic matter took the form of a thin shell around the throat, exerting immense negative pressure, a kind of gravitational repulsion pushing outward to keep the tunnel open. This requirement immediately connected Thorne and Morris's work to deep questions in theoretical physics. The weak energy condition, a long-held assumption in general relativity, states that the energy density measured by any observer should be non-negative. All known forms of classical matter, from hydrogen gas to neutron star material, obey this condition. Their gravity is always attractive. Exotic matter, as defined by the wormhole stability problem, violates the weak energy condition. It has negative energy density. For decades, physicists had considered such matter to be purely hypothetical, a mathematical curiosity with no place in the real universe. Thorne and Morris's work showed that if you wanted a traversable wormhole, you needed this curiosity in vast quantities. Their calculation gave a specific number. The amount of exotic matter required was proportional to the size of the wormhole's mouth. A 1-meter diameter wormhole might require the negative energy equivalent of the mass of Jupiter. This was a staggering requirement, but it was a finite number. It transformed the problem from "is it possible?" to "how could we procure this substance?" More importantly, it forced physicists to ask, does quantum physics allow negative energy densities at all, even in principle? The answer, surprisingly, was yes. Quantum field theory, our most successful framework for particle physics, contains a loophole. While the average energy density of the vacuum is zero or positive with a cosmological constant, local energy densities can fluctuate to negative values due to quantum effects. The most famous demonstration of this is the Casimir effect, first predicted in 1948. Place two perfectly conducting, uncharged metal plates extremely close together in a vacuum. The plates restrict the types of quantum vacuum fluctuations that can exist between them, creating an imbalance. The energy density between the plates becomes lower than the energy density of the free vacuum outside. In effect, the region between the plates has a negative energy density relative to its surroundings. This results in a measurable, attractive force between the plates, experimentally confirmed. The Casimir effect proved that quantum mechanics permits negative energy densities, albeit in exquisitely small amounts and under very specific conditions. The amount of negative energy in a laboratory Casimir setup is minuscule, far less than what would be needed to stabilize a macroscopic wormhole. But the principle was established. Exotic matter was not forbidden by the laws of physics. It was a quantum gravitational resource, scarce and difficult to harness, but real. Thorne and his team had thus accomplished something monumental. They had moved the wormhole from the realm of quantum foam and mathematical curiosities into the domain of theoretical engineering. They had provided a blueprint and identified the necessary, though fantastically rare, building material. Their work was a declaration that traversable wormholes were not logically impossible within the known laws of physics. They were merely, and the merely here is cosmic in scale, an engineering challenge of the highest order. This engineering challenge would soon reveal an even more startling implication. If you could manipulate the mouths of a traversable wormhole, you could manipulate time. The stage was set for the wormhole to reveal its most controversial identity. Not just a shortcut through space, but a potential portal to the past. The Morris Thorne wormhole model was a triumph of theoretical engineering, but it was also a doorway to a deeper, more perplexing realm. By providing a stable blueprint, they had inadvertently constructed a device that threatened the very linearity of time. The moment you have two connected points in space-time that can be moved independently, you have the ingredients for a time machine. This revelation was not a bug in their design. It was a direct consequence of the immutable laws they were attempting to obey, the laws of special and general relativity. Consider a traversable wormhole with two mouths, A and B, initially at rest next to each other. Their clocks are synchronized. Now, take mouth B and accelerate it to a significant fraction of the speed of light, then bring it back to rest near mouth A. According to special relativity, time for the moving mouth B will pass more slowly than for the stationary mouth A. This is time dilation, a well-tested phenomenon. When the journey is over, mouth B's clock will be behind mouth A's clock. They are now at rest in the same location, but they show different times. The wormhole throat provides a direct connection between these 2 points in space-time. If you step into mouth A at, say, 12 p.m. by the local clock, you would emerge from mouth B at the time shown on its clock, which might be 11 a.m. You have not traveled spatially, but you have emerged 1 hour in the past relative to your starting point. By then walking a short distance from mouth B back to mouth A in the external world, you could meet yourself before you entered the wormhole. You have created a closed time-like curve, a path through space-time that returns to its own past. General relativity adds another method. Place one mouth of the wormhole in a region of intense gravity, near a neutron star, for instance. Time passes more slowly in stronger gravitational fields, effect known as gravitational time dilation. The mouth in the high-gravity region will age more slowly than its twin in a weaker field. Again, a permanent time difference is established between the two ends of the same tunnel. The implication was staggering. The Morris Thorne traversable wormhole was not merely a space transport device. It was a potential time machine. This brought theoretical physics face to face with the infamous paradoxes of time travel. The grandfather paradox is the most famous. If you travel to the past and kill your grandfather before your parent is conceived, how could you have been born to travel back in time? It is a logical contradiction that seems to make time travel impossible. Physicists responded not by dismissing time travel, but by asking how physics might resolve such paradoxes. Igor Novikov, a Russian astrophysicist, formulated the principle of self-consistency. He proposed that the laws of physics are inherently consistent and would prevent any action that creates a paradox. If you try to shoot your grandfather, the gun would jam, your aim would fail, or some other intervention would occur. The timeline is fixed and self-consistent. Your presence in the past is already a part of the history that led to your journey. You cannot change the past because your actions are the past. Stephen Hawking took a more prohibitive stance. He proposed the chronology protection conjecture. He argued that the laws of physics, particularly quantum mechanics, contain built-in mechanisms that prevent the formation of closed time-like curves. In the context of a wormhole time machine, he suggested that as you try to create the time difference between the mouths, quantum effects would become dominant. Virtual particles would circulate through the wormhole, looping back in time again and again. With each loop, their energy would build up in a runaway feedback, creating an infinite energy density that would destroy the wormhole before it could be used as a time machine. The best evidence we have that time travel is not possible, Hawking quipped, is that we have not been invaded by hordes of tourists from the future. The debate between self-consistency and chronology protection remains unresolved. It sits at the frontier where classical general relativity intersects with the unknown theory of quantum gravity. Wormholes, therefore, became more than just speculative tunnels. They became crucial theoretical tools for probing the limits of our physical theories, for stress testing the compatibility of relativity and quantum mechanics in the most extreme scenarios. Wheeler's act of naming had set in motion a chain of inquiry that led from the quantum foam to the edge of paradox. The wormhole was no longer just a shortcut. It was a lens focusing our deepest questions about causality, free will, and the nature of time. It forced physicists to consider universes with multiple histories, self-consistent loops, and quantum states that might resolve contradictions. As this chapter closes, we stand at a remarkable point in the story. The ghost of 1935 has been named, quantified, and engineered on paper. It has revealed itself as a potential gateway not just to other stars, but to other times. The practical challenges remain cosmic in scale. The procurement of exotic matter, the stabilization of space-time topology. But the theoretical edifice is robust. The journey of the wormhole concept demonstrates the power of theoretical physics to explore realms beyond empirical reach, to use mathematics as a spaceship for the mind. We have not found a wormhole, but in seeking to understand if they could exist, we have learned profound truths about the universe we inhabit, that spacetime is dynamic, that energy can be negative, that time is elastic, and that the laws of physics are a complex web where solving one puzzle often reveals another, more beautiful and more baffling. So as you listen, let the idea of the wormhole settle not as a promise of travel, but as a symbol of human curiosity. It represents our refusal to accept distance and time as ultimate barriers, our desire to test the fabric of reality against the rigor of mathematics. The tunnel through space and time exists, for now, in the landscape of equations. And in that landscape, it is as real as any star. The Morris Thorne model was a blueprint for a dream, a smooth, traversable tunnel through space-time. But like any grand architectural plan, its viability hinged on the availability of suitable materials. In this case, the required material defied everyday experience. It was not steel or carbon fiber. It was something that seemed to contradict the very behavior of normal matter. This chapter delves into the heart of the wormhole stability problem, exploring the exotic substance that must line its throat, the quantum hints that such a substance might be allowed by nature, and the profound physical laws that stand in the way. To understand why exotic matter is necessary, we must first understand why a wormhole wants to collapse. Imagine the simplest model, a spherical throat connecting two flat regions of space. The throat is a region of extreme curvature. According to general relativity, curvature is synonymous with gravity. The intensely curved walls of the throat possess powerful gravitational self-attraction. They pull inward, like a stretched rubber band snapping back. For a wormhole made of ordinary matter, matter that obeys the classical energy conditions, this inward pull is irresistible. The throat would pinch shut catastrophically, either forming a singularity or severing the connection entirely, faster than even a photon could traverse it. The Einstein-Rosen bridge suffered precisely this fate. The Morris Thorne analysis quantified this problem with elegant precision. They showed that to keep the throat open against its own gravitational crush, the material threading it must exert a tremendous outward pressure. In the language of stress-energy tensors, this translates to a negative energy density. More intuitively, the material must behave as if it has anti-gravitational properties. It must gravitationally repel itself. Physicists have formulated several energy conditions that classify the behavior of matter. The most relevant here are the null energy condition and the weak energy condition. The NEC states that for any light-like vector, the stress-energy tensor must yield a non-negative result. The WEC is stronger, requiring that any observer measuring the local energy density will find it to be non-negative. All known classical forms of matter, from the gas and stars to the degenerate matter in white dwarfs, obey these conditions. Their energy density is positive, and their gravity is attractive. Exotic matter, in the specific technical sense required for wormhole stability, violates the null energy condition. It has a negative energy density as measured by some observers. This is not merely antimatter. Antimatter has positive energy density and generates attractive gravity, just like normal matter. This is also not dark matter, whose gravitational effects suggest it too has positive energy density. Exotic matter is something far stranger, a substance whose very presence creates a local gravitational repulsion. For decades, such matter was considered mathematical impossibility, a sign that a given spacetime geometry was unphysical. The Morris-Thorne work turned this logic on its head. They demonstrated that if you want a traversable wormhole, you must have NEC-violating matter. The requirement was not optional. It was baked into the geometry of a stable throat. The question then shifted from, does this geometry require exotic matter, to does physics permit exotic matter at all? The answer, surprisingly, comes from quantum mechanics. While the classical average properties of matter obey the energy conditions, quantum field theory allows for local and temporary violations. These are not violations of fundamental law, but rather manifestations of quantum uncertainty. The energy density at a point in a quantum field can fluctuate to negative values as long as the average over a sufficient volume remains positive. This is the quantum loophole. The most famous and experimentally verified demonstration of this loophole is the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that two perfectly conducting, uncharged plates placed very close together in a vacuum would experience a faint attractive force. The explanation is purely quantum. The vacuum is not empty. It is a seething sea of virtual particle pairs that constantly flicker in and out of existence, borrowing energy from the vacuum via the uncertainty principle. These virtual particles create a background of quantum fluctuations in all fields, including the electromagnetic field. The plates impose a boundary condition. Only certain wavelengths of virtual photons can fit between the plates, while all wavelengths are allowed outside. This restricts the possible quantum fluctuations in the gap between the plates, resulting in a lower energy density there compared to the energy density of the free vacuum outside. The energy density between the plates becomes negative relative to the external reference. This energy difference manifests as a pressure, pushing the plates together, an attractive Casimir force. The effect has been measured with remarkable precision in modern laboratories. The Casimir effect is a direct laboratory proof that quantum mechanics permits localized regions of negative energy density. It is exotic matter in a tangible, if microscopic, form. However, the scale is inconceivably small compared to the needs of a Morris-Thorne wormhole. The negative energy in a Casimir setup is proportional to hc/d, where d is the plate separation. For plates 1 micrometer apart, the effect is tiny. To stabilize a 1-meter wormhole throat, Calculations suggest you would need to concentrate a Jupiter mass worth of such negative energy into that region. The challenge, therefore, is not one of principle, but of magnitude and engineering. Can quantum effects be harnessed and amplified to produce macroscopic amounts of negative energy density? Some speculative theories suggest that certain configurations of intense electromagnetic fields or quantum states of matter, like Bose-Einstein condensates, might amplify Casimir-like effects, but these remain highly speculative. The gap between the microscopic permission granted by quantum mechanics and the macroscopic requirement for a traversable wormhole is arguably the greatest chasm in this entire theoretical edifice. This requirement for exotic matter does more than just define a technological hurdle. It ties the fate of the traversable wormhole to the deepest unresolved questions in physics: the nature of the quantum vacuum, the possibility of manipulating spacetime topology, and the ultimate validity of the energy conditions. The wormhole has become a probe, its stability a test for the existence of macroscopic exotic matter. If such matter is forever confined to the quantum realm, then traversable wormholes may be forever confined to the pages of theory and science fiction. The Casimir effect provides a crucial proof of principle, but it is a whisper where a shout is needed. Bridging the gap between those microscopic quantum whispers and the macroscopic shout required to hold open a wormhole throat leads us into the realm of speculative quantum engineering and alternative theories of gravity. The search for viable mechanisms to generate or substitute for exotic matter has spawned some of the most creative and controversial ideas in theoretical physics. One avenue explores the possibility of engineering the quantum vacuum itself. The Casimir effect arises from restriction of vacuum modes. Could more elaborate geometries, arrays of plates, microscopic structuring, or intense electromagnetic field configurations create regions of enhanced negative energy density? Concepts like the Casimir battery have been proposed, where energy is theoretically stored in the form of arranged vacuum states. However, calculations consistently show that the amounts produced are minuscule, bound by so-called quantum inequalities that limit the magnitude and duration of negative energy density. These inequalities suggest that nature imposes a tax. You can borrow negative energy, but you must pay it back quickly, and you can never borrow very much at once. This seems to forbid the sustained, colossal negative energy density needed for a human-sized wormhole. This leads to a more radical question. Must we rely on exotic matter at all? Could the laws of gravity themselves be different, allowing wormholes made of normal stuff? This is the domain of modified gravity theories. Einstein's general relativity is our best theory of gravity, but it is not the only possible one. Theories like scalar tensor gravity, brane-world scenarios, or extensions involving higher dimensions sometimes contain solutions for traversable wormholes without exotic matter, or with milder forms of it. In these theories, the extra fields or dimensions provide additional repulsive forces that can counteract the throat's collapse. However, these theories remain unproven, and their predictions must still align with a vast array of precise tests that general relativity has passed. No modified theory has yet gained widespread acceptance as a replacement. Perhaps the most profound connection is between wormholes and the other great prediction of general relativity, black holes. In the 1990s, a startling idea emerged from the study of black hole thermodynamics and information. The Einstein-Rosen bridge, the original non-traversable wormhole, is mathematically similar to the maximally extended spacetime of a Schwarzschild black hole, which includes a theoretical white hole and a separate universe. In this picture, falling into a black hole might theoretically connect you to another region of spacetime via the bridge, but the crushing singularity makes it non-traversable. Modern research, fueled by the holographic principle and string theory, has taken this further. The ER equals EPR conjecture, proposed by Juan Meldacena and Leonard Susskind in 2013, posits a deep duality. An Einstein-Rosen bridge, ER, connecting two black holes is equivalent to a pair of quantum entangled particles, EPR. In this view, the wormhole is not a separate structure. It is the geometric manifestation of quantum entanglement. The connectivity of spacetime itself might be woven from these quantum threads. This doesn't immediately give us a traversable wormhole, but it suggests that the ingredients for spacetime tunnels are fundamentally quantum and ubiquitous at a microscopic level. For a wormhole to be traversable in this quantum context, the entanglement would need to be manipulated and amplified in a specific way. Some recent theoretical work, notably by Ping Gao, Daniel Jeffries, and Aaron Wall, has shown that by creating a special kind of quantum coupling between two black holes, one might make the wormhole connecting them temporarily traversable. This traversable wormhole would be microscopic and short-lived, but it would be created using quantum information techniques rather than mythical exotic matter. It represents a bridge between the world of quantum information theory and space-time geometry. Yet, even these dazzling theoretical advances underscore the monumental challenge. The wormholes of ER equals EPR are Planck scale or involve black holes. Scaling them up to macroscopic, human traversable dimensions remains a problem of astronomical, or more accurately, universal proportions. The energy scales involved are those of quantum gravity, far beyond any conceivable technology. The requirement for exotic matter, or its theoretical equivalence, thus serves as a cosmic reality check. It places the traversable wormhole at the very edge of physical plausibility. It tells us that if such tunnels exist in nature, they are either natural and microscopic, woven into the quantum foam of space-time, forever beyond our access, require a mastery of physics and engineering so far beyond our current understanding that it is indistinguishable from magic. The ability to manipulate the vacuum state on planetary scales, or to control quantum entanglement between macroscopic objects. This does not render the study of wormholes futile. On the contrary, it elevates them. The wormhole has become a theoretical laboratory. By demanding exotic matter, it forces us to examine the limits of quantum field theory and the energy conditions. By connecting to entanglement via R equals EPR, it provides a stunning geometric picture of quantum non-locality. By threatening to create time machines, it pushes us to refine our understanding of causality. The stability problem is therefore not a dead end, but a signpost pointing toward the deepest mysteries of the universe: the quantum structure of spacetime, the nature of gravity, and the relationship between information and geometry. The quest for exotic matter is, in essence, a quest to understand whether the fabric of reality can be persuaded to knit itself into a tunnel. The answer remains hidden in the unresolved union of quantum mechanics and general relativity. As we ponder this, the wormhole transforms from a mere shortcut to a symbol. It represents the ultimate challenge of theoretical physics: to reconcile the very large with the very small, and to understand if the cosmos, in its deepest laws, permits such breathtaking shortcuts. The exotic matter is the key, and that key is locked in a vault whose combination we are only beginning to guess. The search for exotic matter and stable wormhole solutions is more than an intellectual exercise in extreme geometry. It is a pressure test for our most fundamental theories of reality. Each proposed workaround, from modified gravity to quantum entanglement, reveals a new facet of the profound difficulty and the profound allure of the problem. As we reach the limits of known physics, the wormhole also forces us to confront philosophical and practical boundaries, the nature of causality, the limits of technological aspiration, and the very definition of what is physically possible. Consider the implications of truly mastering exotic matter. If a civilization could produce and manipulate macroscopic quantities of negative energy density, its power would extend far beyond creating wormholes. Such a technology would imply control over gravity itself. One could in principle design anti-gravitational devices, stabilize otherwise unstable spacetime structures, or even influence the expansion of the universe locally. The energy conditions, long considered bedrock principles, would become engineering parameters. The civilization wielding this power would operate on a cosmological scale, literally bending the rules of reality to its will. This is a threshold so far beyond our current capabilities that it resides firmly in the realm of Type 3, or beyond on the Kardashev scale, a signature of a mastery over galactic resources and physics. Yet, even if such power were attainable, the wormhole stability is only the first hurdle. The moment you have a stable, traversable wormhole, you have also created a potential time machine, as explored in the previous chapter. This reintroduces the paradoxes with renewed urgency. Would the self-consistency principle hold, or would the chronology protection conjecture kick in, perhaps through a mechanism even more dramatic than quantum vacuum collapse? Some theories suggest that the very act of making a wormhole traversable might automatically trigger instabilities that either destroy it or prevent the creation of closed time-like curves. The stability problem and the time travel problem may be inextricably linked, two sides of the same coin minted in the realm of quantum gravity. This leads to a sobering, yet fascinating possibility. Perhaps traversable wormholes are not just difficult to build. Perhaps they are fundamentally impossible in a consistent universe. The cosmic censorship hypothesis, which suggests that singularities are always hidden behind event horizons, might have a counterpart, a topological censorship theorem. Such a principle would state that the laws of physics prevent the formation of causal loops and macroscopic non-trivial topology that could lead to paradoxes. In this view, every attempt to construct a traversable wormhole would inevitably fail. The throat would collapse. Exotic matter would prove unstable at large scales, or quantum effects would sever the connection. The universe might simply forbid such shortcuts to preserve causal order. However, the relentless engine of theoretical physics continues to probe these limits. The ER equals EPR conjecture and related work in holography have opened a new window. They suggest that the building blocks of spacetime connectivity are everywhere, in the form of quantum entanglement. The wormhole is no longer a separate, gross object to be constructed, but a latent property of quantum information that might be activated or grown under the right conditions. This shifts the paradigm from one of colossal engineering to one of exquisite quantum control. It is a shift from bulldozing space-time to coaxing it. The practical challenges, of course, remain astronomical. Manipulating quantum entanglement on a scale sufficient to influence macroscopic geometry is currently unimaginable. It would require a quantum gravity device of unprecedented power, perhaps harnessing the energy of stars to manipulate Planck-scale phenomena. Yet, the theoretical possibility is revolutionary. It suggests that the universe is, at its heart, a network of quantum connections, and that what we perceive as separated points in space may be intimately linked in a higher dimensional information space. The wormhole, in this light, is not an anomaly, but an expression of the universe's underlying connectedness. As we conclude this chapter on stability and exotic matter, we are left not with a solution, but with a deeper appreciation of the problem. The wormhole has guided us through a landscape of quantum field theory, general relativity, modified gravity, and quantum information. It has shown us where our theories strain and where they might break. It has forced us to question cherished assumptions about energy and causality. For you, the listener, let this not be a story of disappointment, but of wonder. The fact that we can pose these questions so precisely, that we can use mathematics to explore realms beyond our senses, is a triumph of the human mind. The wormhole may forever remain a ghost in the equations, but it is a ghost that has taught us profound truths about the living cosmos. The dream of a stable tunnel through space and time endures because it speaks to a fundamental human desire to overcome barriers, to connect, to explore. Even if the universe ultimately says no to traversable wormholes, the journey to understand why has already expanded our vision of reality. We have learned that space is dynamic, that energy can be negative, that entanglement might weave the fabric of distance, and that time is far more elastic than our daily experience suggests. Now, as we prepare to move from the problem of stability to the even more mind-bending consequences of time manipulation, carry with you this understanding. The greatest value of the wormhole concept may not be as a potential transportation device, but as a catalyst for discovery. It is a question that, in the asking, reveals the stunning architecture of physical law, that a stable, traversable wormhole is more than a gateway to distant stars. As Kip Thorne and his students realized, it is a potential instrument for navigating time itself. This revelation pushes the discussion from the challenging physics of exotic matter into the profound and perplexing realm of causality. This chapter explores the consequences of wormhole time machines, the logical paradoxes they unleash, and the fierce intellectual battle among physicists to either resolve these paradoxes or use them to prove such machines cannot exist. The mechanism for creating a time machine from a wormhole is elegantly simple in principle, relying on the uncontested pillars of special and general relativity. Time dilation. Take a traversable wormhole with two mouths, A and B, initially together with synchronized clocks. Now, move mouth B on a high-speed journey. According to special relativity, time for the moving mouth will pass more slowly. When it returns and is parked next to mouth A again, its clock will be behind. The wormhole throat now connects 2 points in space that are also 2 different points in time. Entering mouth A at 3 p.m., you exit mouth B at, say, 2 p.m. You have traveled 1 hour into your own past. In the language of general relativity, such a configuration creates a closed time-like curve, a CTC. This is a path through spacetime that, if followed, returns you to your own past. The region containing the CTC is a time machine. The moment the time difference between the wormhole mouths is established, every point in the external region near the mouths becomes connected to its own past via a short trip through the tunnel. The immediate and famous consequence is the grandfather paradox. Imagine using such a wormhole to travel back to a time before your father was conceived. You find your grandfather and prevent him from meeting your grandmother. This action erases your father's birth, and consequently your own. But if you were never born, who traveled back in time to intervene? The sequence of events is logically self-contradictory. It violates the foundational principle of cause preceding effect. Physics abhors such logical inconsistencies. If general relativity seems to permit time machines via wormholes, but logic and experience forbid paradoxes, then something must give. Either our understanding of the physics is incomplete, or nature has mechanisms to prevent paradoxes from occurring. Theoretical physicists have split into camps pursuing each of these possibilities with vigor. The first major response is the principle of self-consistency, championed by Russian physicist Igor Novikov. Novikov proposed that the laws of physics are intrinsically consistent and will not allow paradoxes to happen. If you attempt to create a paradox, something will always intervene to make your actions part of a single, consistent history. You might travel back in time, but you will find yourself unable to change the past in a contradictory way. Your gun will jam. You will slip on a banana peel. You will, at the last moment, choose not to pull the trigger. The timeline is fixed and self-consistent. Your presence in the past was always a part of that past. In this view, time travel is possible, but it is a journey into a past that already includes your visit. You are an actor following a script you cannot change, even if you think you have free will. Novikov's principle is elegant, but philosophically unsettling. It suggests a form of determinism so powerful that even a time traveler with apparent agency is bound by the immutable history they are part of. It turns the universe into a static, four-dimensional block where all events, past, present, and future coexist. Time travel in such a universe is not about changing history, but about fulfilling it. The opposing camp, led most famously by Stephen Hawking, argues that nature is more protective of causality. Hawking proposed the chronology protection conjecture. He asserted that the laws of physics, particularly quantum effects, will always act to prevent the formation of CTCs. A time machine will never become operational because some physical process will destroy it first. In the context of a wormhole time machine, Hawking and others calculated that as you try to create the time difference between the mouths, the quantum vacuum would react catastrophically. The proposed mechanism is a feedback loop of virtual particles. As the mouths approach a configuration that creates a CTC, virtual particle-antiparticle pairs could form at one mouth, travel through the wormhole to the other mouth emerging in the past, and then travel back externally to the first mouth, arriving before they initially formed. They could then interact with themselves, influencing their own creation. This closed loop could lead to a runaway buildup of energy. The quantum vacuum fluctuations would diverge to infinity, creating an unsustainably large energy density at the wormhole throat. This energy would either destroy the wormhole or warp spacetime so severely that the time machine configuration becomes impossible to achieve. Nature, in this view, uses quantum mechanics to erect a shield around causality, making time travel to the past physically impossible, not just logically tricky. Hawking playfully called this the court of law approach to chronology protection. The best evidence that time travel to the past is impossible is the absence of tourists from the future. If time machines were ever invented, he reasoned, someone would eventually use one to come back and reveal themselves. Since we see no convincing evidence of time travelers, time machines likely cannot be built. The battle between self-consistency and chronology protection is not merely academic. It strikes at the heart of our understanding of time, free will, and the relationship between quantum mechanics and general relativity. Wormholes, by providing a concrete theoretical model for a time machine, have become the primary battleground for this conflict. The conflict between self-consistency and chronology protection represents a deep schism in how we conceive of physical law. Is the universe a self-correcting, consistent narrative where paradoxes are logically impossible, or is it a system with built-in safety features that actively thwart any attempt to tamper with causality? To move beyond philosophical preference, physicists have sought to model these scenarios mathematically, using the wormhole time machine as their test case. The results venture into the bizarre, challenging our notions of computation, probability, and even the meaning of a physical state. One approach to modeling self-consistent time travel uses the concept of quantum mechanics interacting with closed time-like curves. Instead of a macroscopic grandfather, consider sending a single quantum particle, a photon, through a wormhole time machine so that it emerges in its own past. Could it interact with its earlier self in a way that creates a paradox? In the 1990s, theorists like David Deutsch proposed that quantum mechanics, with its inherent probabilities, might provide a natural framework for consistency. In the Deutsch model, a quantum particle enters a CTC. Its earlier self and its later self interact. The outcome must be consistent. The state of the particle when it exits the wormhole must be exactly the state that, after the interaction and journey, leads it to enter the wormhole in that same state. This is a fixed-point condition. Deutsch showed that quantum mechanics, unlike classical logic, always admits at least one consistent solution to such problems. The universe doesn't produce a paradox. It settles into one of several possible consistent probability distributions. In this quantum view, time travel doesn't lead to logical contradiction, but to a peculiar mixing of quantum states that enforces self-consistency. It suggests that if time machines exist, they operate under quantum rules that inherently prevent classical paradoxes. However, this quantum consistency comes at a potentially steep price. Some calculations suggest that the allowed consistent solutions can involve bizarre states, like particles being in a mixture of existing and not existing, or can lead to computational power so great that it breaks our standard understanding of complexity theory. This has led some to argue that the mere existence of such bizarre consequences is proof that nature forbids CTCs, a form of the chronology protection conjecture based on computational or informational grounds. Hawking's original chronology protection conjecture based on vacuum fluctuations has also undergone refinement. Further calculations by others showed that the predicted energy divergence might be sensitive to specific conditions and might not always occur. In some wormhole models, or in the presence of certain quantum fields, the vacuum energy might remain finite. This has led to an ongoing technical battle. For every proposed model of a time machine, others search for a quantum effect that will destabilize it. The consensus remains elusive, but the sheer difficulty of constructing a stable, paradox-free time machine in any detailed model suggests that nature has many ways to say no. Beyond the quantum vacuum, other protective mechanisms have been proposed. The principle of topological censorship suggests that the laws of gravity itself might prevent the formation of causal loops accessible to observers. In many solutions of general relativity that contain CTCs, like the interior of a rotating black hole, Kermetric, or the Gödel universe, the curves are hidden behind event horizons or are not traversable in a stable, controlled way. Perhaps any attempt to create a traversable CTC inevitably leads to a configuration that is either hidden from the universe or collapses. The wormhole time machine also forces us to reconsider the nature of time. The block universe view of eternalism, where past, present, and future all equally exist, is naturally compatible with self-consistency. In this view, the time traveler was always part of the past. Their journey is just a thread woven into the four-dimensional tapestry. The presentist view, that only the present is real, struggles profoundly with the concept. If the past is gone and the future is not yet real, what does it mean to travel to a place that doesn't exist? This is not just metaphysics. Our best physical theories, special and general relativity, are deeply eternalist. They treat space-time as a single, unchanging geometric object. The wormhole time machine is a natural, if extreme, feature of this geometry. To ban it requires adding a new law or principle on top of relativity, like chronology protection. The debate, therefore, is about whether we need to supplement our fundamental theories with additional causality protecting axioms. As you absorb these competing ideas, a middle ground emerges. Perhaps the answer is not a stark yes or a no, but a yes, but yes, the equations might permit time travel under extraordinarily specific and contrived conditions, conditions that require matter states beyond our current understanding and control over quantum gravity. But those very conditions may be so unstable, so sensitive to perturbation, that they are effectively impossible to realize in a noisy quantum universe. The time machine might exist in the Platonic realm of perfect mathematics, but be forever inaccessible in the physical universe of approximation and fluctuation. This leads us to a pragmatic, though no less wondrous, conclusion. The study of wormhole time machines is invaluable not because it will lead to a working prototype, but because it stresses our theories to the breaking point. By asking if we can build a time machine, we learn what our theories truly say about time, causality, and the structure of reality. We are using the dream of time travel as a diagnostic tool for the health of physics itself. The debate over wormhole time machines and their paradoxes does not conclude with a definitive answer. Instead, it opens into a broader vista of questions about the fundamental architecture of reality. Whether one sides with Novikov's consistency or Hawking's protection, the very exercise of building these theoretical models has yielded profound insights that ripple across modern physics from quantum gravity to the philosophy of science. This final part of our chapter explores these wider implications and what they mean for our place in a potentially time-travel-capable cosmos. The struggle to reconcile closed time-like curves with quantum mechanics has fertilized the field of quantum information theory. The Deutsch model, where quantum states self-consistently interact on CTCs, is not just a curiosity. It has become a tool for thought experiments about computation and communication. Researchers have explored post-selected time travel, a model where you only consider experimental runs that are self-consistent, throwing away the paradoxical ones. This model, while not describing physical time travel, has been shown to enable surprising computational feats in theory, solving certain problems exponentially faster than standard quantum computers. It suggests a deep link between causality, computation, and the flow of information in the universe. Perhaps the most significant impact of the wormhole time machine debate has been its role in the development of the holographic principle and the ADS/CFT correspondence. This is a concrete realization in string theory, where a gravitational theory in an anti-de Sitter spacetime is equivalent to a conformal field theory on its boundary, a kind of quantum gravity in a box being described by a non-gravitational quantum theory on the box's walls. In this framework, wormholes and their causal structures are mapped onto intricate patterns of quantum entanglement in the boundary theory, the ER equals EPR conjecture, positing that entangled particles, EPR pairs, are connected by microscopic Einstein-Rosen bridges, emerged from this milieu. Here, the wormhole is not a time machine, but a geometric manifestation of quantum correlation. This idea provides a stunningly beautiful resolution to one aspect of the information paradox. Information that falls into two entangled black holes might not be lost, but transmitted through the wormhole connecting them. While these are not traversable wormholes in the classic sense, they represent a paradigm shift. Space-time connectivity and causality may not be primary, fundamental concepts, but rather emergent phenomena from a more basic quantum substrate of information and entanglement. This perspective subtly changes the time travel question. If space-time is emergent from quantum entanglement, then perhaps closed time-like curves represent not a breakdown of causality in the fundamental theory, but a breakdown of the geometric description itself, a sign that the emergent spacetime picture is failing, much like a map distorting at the poles. The true, fundamental quantum theory may have no concept of time travel at all. The paradoxes may be artifacts of trying to force a smooth geometric narrative onto a quantum reality, where before and after lose their sharp meaning. For the contemplative mind, this journey through paradox leads to a place of humility and awe. We began with a simple, if fantastical, idea, a tunnel through space that could also become a tunnel through time. We encountered logical impossibilities that seemed to rule it out. Then we explored how physics might bend to avoid these impossibilities, either through deterministic self-consistency or through active quantum protection. Finally, we see the concept dissolving into the deeper waters of quantum gravity, where time and space themselves may be secondary, emergent properties. The wormhole time machine, therefore, serves as a lighthouse. It marks the treacherous boundary where our two great theories, the quantum and the relativistic, meet and clash. Its paradoxical glare illuminates the limitations of our current understanding. We cannot yet say if such machines are possible, because we do not yet have the theory that governs the regime where they would exist. Their study is a guidepost pointing toward the necessary features of a theory of quantum gravity. It must somehow resolve or forbid causal paradoxes. As you prepare to leave this chapter, let go of the need for a simple answer. Instead, hold on to the richness of the questions. The fact that we can so precisely articulate the grandfather paradox within the framework of general relativity is a testament to the power of the theory. The fact that we can use quantum mechanics to probe potential resolutions shows the flexibility of our tools. We are like cartographers mapping an unknown coastline, using paradoxes as sounding lines to measure the depth of our ignorance. The dream of time travel, sparked by the wormhole, may never be realized in the way science fiction imagines. But in chasing that dream, we have been forced to invent new mathematics, conceive of new physical principles, and deepen our understanding of time, causality, and information. That is a victory far greater than any single invention. It is the victory of curiosity over complacency, of reason over assumption. So tonight, as you drift toward sleep, think not of paradoxes as walls, but as doors. The grandfather paradox is not a stop sign. It is an invitation to think more deeply about cause and effect. Hawking's chronology protection is not a death knell for wonder. It is a hypothesis about the universe's steadfast rules. And the serene, consistent block universe of Novikov is not a prison of determinism, but a vision of a cosmos where every event has its necessary place, woven into a whole of breathtaking geometric logic. The wormhole has taken us to the edge of time and shown us the chasm beyond. We may not cross it, but in looking across, we have seen further than ever before. We have journeyed from Einstein's geometric ghost to the precipice of time paradoxes. We stand now at the modern frontier, where the wormhole is undergoing its most profound transformation. It is no longer merely a speculative tunnel or potential time machine. In the cutting-edge theories of 21st century physics, the wormhole is becoming something more fundamental, a key to understanding the quantum fabric of spacetime itself, and perhaps a guide to the ultimate unification of physics. This final chapter explores that transformation. The pivotal shift began with the holographic principle, first suggested by Gerard T. Hooft and later refined by Leonard Susskind. It proposes that all the information contained within a volume of space can be represented as a theory living on the boundary of that space, like a three-dimensional hologram encoded on a two-dimensional surface. This radical idea found a precise mathematical realization in the anti-de Sitter/conformal field theory correspondence proposed by Juan Meldacena in 1997. AD/CFT is a duality, a theory of quantum gravity in a certain curved spacetime is completely equivalent to a non-gravitational quantum field theory on its lower dimensional boundary. Within the framework of AD/CFT, wormholes found a new and stunning role. In 2013, Meldacena and Susskind made a bold conjecture, ER equals EPR. An Einstein-Rosen bridge, a wormhole, is equivalent to a pair of quantum-entangled particles, an Einstein-Podolsky-Rosen pair. This was not just an analogy. They proposed it as a fundamental identity. The spatial connection of a wormhole is the geometric manifestation of quantum entanglement. When two black holes are entangled, they are connected by a wormhole. The more entanglement, the shorter and more connected the wormhole. This idea turns intuition on its head. We normally think of space as the primary stage and entanglement as a strange relationship between actors on that stage. ER equals EPR suggests the reverse. Entanglement might be the primary substance, and space, including wormholes, is how that entanglement looks when we perceive it geometrically. A universe where everything is entangled might be a universe that is spatially connected in a complex, wormhole-riddled network. What we perceive as vast, empty distances could, at a fundamental level, be woven from countless threads of quantum correlation. This has profound implications for the black hole information paradox. Information that falls into one of a pair of entangled black holes might not be lost. It could be transmitted through the microscopic wormhole, the ER bridge, to its partner, preserving the overall quantum information of the system. The wormhole becomes a rescue mechanism for unitarity, the principle that quantum information is never destroyed. But what about traversable wormholes for humans? The ER bridges in these models are typically non-traversable. They are incredibly fragile, pinching off if you try to send a signal through. However, recent theoretical work has shown that by manipulating the quantum entanglement, specifically by performing a particular kind of measurement on the boundary theory, the wormhole can be made temporarily traversable. In 2019, Ping Gao, Daniel Jeffries, and Aaron Wall demonstrated this in a theoretical model. They showed that by creating a specific quantum coupling between the two boundary theories, representing the two mouths of the wormhole, you could send a signal through the geometric bridge. It would be a microscopic, fleeting event, but it proved a principle. Traversability is linked to specific, sophisticated quantum operations on the entangled states. This is light years from a stargate. It is more akin to using the universe's deepest quantum code to briefly open a channel between 2 points, yet legitimizes the wormhole as a dynamical object in quantum gravity, not just a static solution. It suggests that the difference between a disconnected space and a wormhole-connected space is not in the gross arrangement of matter, but in the pattern of quantum information. Concurrently, other branches of quantum gravity, like loop quantum gravity, also find room for wormhole-like structures, spacetime defects, or quantum tunnels that could have formed in the extreme density of the early universe. Some cosmologists speculate that the entire universe's large-scale structure might be seeded by a primordial froth of quantum wormholes, inflated to cosmic scales during the Big Bang. Others ponder if dark energy or other cosmological puzzles hint at a space-time microstructure laced with such topological features. The wormhole, once a lonely outpost of general relativity, is now a bustling crossroads where gravity, quantum mechanics, and information theory meet. Its study is no longer about dreaming of interstellar shortcuts. It is about decoding the source code of reality. The theoretical fusion of wormholes with quantum entanglement represents a monumental leap in understanding, but it raises an equally monumental question. Could we ever observe a wormhole? If they are not mythical cosmic shortcuts, but potentially fundamental features of space-time's quantum architecture, might there be an observational signature, a way to detect their presence indirectly? This quest moves the wormhole from the pages of theory to the realm of observational astronomy, albeit at the very limits of possibility. One promising avenue involves the shadow of a black hole. The Event Horizon Telescope's image of M87* revealed a dark shadow surrounded by a bright ring of lensed light. Theorists have calculated what the shadow of a black hole connected to a wormhole might look like. Depending on the wormhole's geometry, the shadow could appear distorted, have a double silhouette, or be surrounded by secondary rings of light caused by photons that traveled through the wormhole throat. Comparing high-fidelity future EHD images with these theoretical templates could, in principle, reveal the presence of a wormhole mouth disguised as a black hole. It would be a subtle fingerprint in the pattern of light, requiring immense resolution and precision. Another potential signature is gravitational lensing. A wormhole mouth would have a powerful gravitational field, bending light from background stars and galaxies. However, unlike a black hole of the same mass, a wormhole might lack an event horizon, allowing light to pass through the throat and emerge from the other mouth. This could create bizarre lensing patterns, duplicate distorted images of the same background object appearing in two different parts of the sky, with no massive visible object in between to explain one of them. Astronomers already use gravitational lensing to map dark matter, searching for anomalous, unexplained lensing events could be a wormhole hunting strategy. The most dramatic potential detection method involves studying binary systems. If a wormhole mouth behaves like a massive, dark object, it could exist in a binary orbit with a normal star, much like the black hole in Cygnus X1. By measuring the star's orbit, we could infer the mass of its dark companion. If that mass falls within the mass gap between neutron stars and black holes, or if other peculiarities arise, such as a lack of X-ray emission from an accretion disk where it should be present, it could hint that the dark object is not a black hole but something else, perhaps a wormhole mouth. More speculatively, if we could ever measure the tidal love numbers of a compact object, how its shape deforms in a gravitational field, a wormhole and a black hole might differ. Then there's the possibility of detecting a wormhole through its effect on quantum systems. If ER equals EPR is correct and macroscopic wormholes correspond to specific large-scale entanglement, then perhaps the structure of spacetime itself influences quantum correlations over large distances. This is currently far beyond our experimental reach, but it points to a future where quantum sensors distributed across space might one day map the subtle entanglement geometry of the cosmos, indirectly revealing its wormhole structure. However, the greatest constraint on observable wormholes likely comes from their stability requirement: exotic matter. If exotic matter with macroscopic negative energy density does not exist in nature, then traversable wormholes likely do not exist either. Our best evidence for exotic matter remains the microscopic Casimir effect. Unless a natural macroscopic source of such matter is discovered, perhaps in the form of a cosmological field or a phase of matter in the early universe, wormholes may only exist as Planck-scale fluctuations in the quantum foam or as non-traversable ER bridges between entangled particles. This brings us to the ultimate role of the wormhole in modern physics as a theoretical bridge. It bridges the concepts of geometry and information. It bridges the classical world of general relativity and the quantum world. It even bridges different domains of theoretical physics, from string theory and holography to loop quantum gravity and cosmology. By studying the extremes required to make a wormhole, exotic matter, manipulation of entanglement, avoidance of paradoxes, we learn what a complete theory of quantum gravity must be able to explain or forbid. The wormhole has become a theoretical laboratory. We perform thought experiments within it to stress test our ideas. Can information escape a black hole via a wormhole? Does quantum mechanics resolve time travel paradoxes? Is space-time fundamentally emergent? The wormhole provides a concrete, if fantastical, setting to pose these questions with mathematical rigor. As we approach the conclusion of our story, it is clear that the wormhole's journey mirrors the journey of physics itself. It began as a clear, classical geometric object. It encountered the quantum revolution and was relegated to the realm of impossibility due to instability. It was resurrected by the ingenuity of theorists who found loopholes and blueprints. Finally, it is being subsumed into a new, deeper understanding where it is not an object in space, but an expression of space's underlying quantum nature. We have not found a wormhole. We may never use one as a shortcut, but in seeking them, we have been forced to invent powerful new concepts, to confront the paradoxes of time, and to glimpse a universe where space, time, and information are woven into a single, breathtaking tapestry. The search for the cosmic shortcut has, ironically, taken us on the longest journey of all, into the heart of physical reality. Our journey ends not with the discovery of a stargate, but with a deeper, more resonant understanding. The wormhole has transcended its origins as a science fiction trope to become a cornerstone of theoretical thought, a lens through which we examine the deepest principles of the universe. As we conclude this exploration, we reflect on what the wormhole truly represents, not a promise of travel, but a promise of understanding. The modern wormhole, as defined by ER equals EPR and holography, suggests a reality where separation is an illusion. Two particles entangled across the galaxy are, in a geometric sense, adjacent. The vast distances of space may be woven from countless such threads of connection. This is a profoundly unifying vision. It hints that the cosmos is not a collection of isolated objects in a void, but a single, intricately connected quantum system whose perceived geometry emerges from a network of relationships. The wormhole is the emblem of that connection. This perspective reshapes our biggest questions. The search for a theory of quantum gravity is, in part, the search for the rules that govern this network. The wormhole sits at the center of this search because it is the simplest geometric manifestation of non-trivial connectivity. By understanding how wormholes form, stabilize, and evolve in a quantum theory, we learn how spacetime itself knits itself together. Furthermore, the wormhole forces a reckoning with information. The black hole information paradox asked, does information vanish forever behind an event horizon? The wormhole, in its modern entangled form, offers a potential escape route, not for spaceships, but for quantum bits. Information might be preserved through cosmic connections, invisible to the classical eye. This isn't just about saving data. It's about preserving the unitarity and determinism that underpin all of quantum physics. The wormhole becomes a guardian of cosmic logic. For you, the listener, this knowledge offers a unique form of peace. In a world that often feels fragmented and disconnected, physics whispers a secret. At the most fundamental level, everything is linked. The space between stars, between you and the person next to you, between the past and the future, may be filled not with emptiness, but with a vibrant, invisible lattice of potential connections. The wormhole is the symbol of that latent connectivity. You are not an isolated observer in a cold universe. You are a node in a cosmic web of staggering complexity and beauty. The practical dream of wormhole travel may forever remain a dream. The exotic matter requirements, the quantum fragility, the causal paradoxes, these are formidable, perhaps insurmountable barriers. But this is not a failure of imagination. It is a triumph of reason. We have followed an idea to its logical extremes and discovered that the universe is richer and more mysterious for placing such wonders just beyond our reach. They exist as possibilities in the equations, as guides for our theories, and as eternal reminders that reality is stranger than fiction.so. As you drift into sleep tonight, let go of the need for a tunnel to other stars. Instead, embrace the deeper truth the wormhole has revealed. Our universe is a geometric marvel, a quantum puzzle, and an informational masterpiece. The same laws that might permit a wormhole also ensure the consistency of time, the preservation of information, and the breathtaking regularity of the cosmos. You are living within those laws. Your consciousness is experiencing a tiny fragment of this magnificent, coherent whole. The story of the wormhole is the story of human curiosity pushing against the boundaries of the knowable. From Einstein's equations to Wheeler's naming, from Thorne's engineering to Meldesena's duality, each step has expanded our vision. We have not built a shortcut through space, but we have built a bridge of understanding across the chasms, between gravity and quantum mechanics, between space and information, between the possible and the impossible. Now, as this final chapter closes, allow the concepts to soften. Release the images of swirling tunnels and time paradoxes. What remains is a single, powerful feeling. The feeling of being part of a cosmos that is knowable yet full of wonder, vast yet deeply connected, governed by rules that allow for dreams as wild as wormholes, yet stable enough to cradle life and consciousness. The cosmic shortcut we sought was not through space, but through understanding, and in that we have succeeded beyond measure. Good night.